Good morning. So my partner in crime in this is Chris Berge, who just got introduced. I'm an engineer. As any self-respecting engineer, I'm the cost center. Chris is the guy who makes the money. So I get to state all the problems and have all the fun, and I'll have him come over here to talk about what he is going to do with all these technologies. Let's get back to the flash industry. It's been a little bit of a difficult, choppy ride. As Tour de France goes, where they have the fun going down, we probably are going to have a little bit more fun going back up again. This is the Pyrenees part of the ride coming up. You can see actually the drop from 2017 to the high to where we dropped in 2019 is probably a lot more steep, even on a percentage basis compared to 2008. You remember how tough it was? So the fact that we have weathered through this and we are at the bottom of the trough looking up, Forward Insights puts that projection up in front saying it's going straight up from there. Okay, we're all back here, let's figure out how to get back up out of this, right? So where is that optimism coming from? Clearly, there is a lot of data being created. 32 zettabytes last year, zooming to over 100 zettabytes. And this zooming into the zettabyte age, we require a different way of looking at things. We look at it in three phases. The endpoints, where all this data is being created. Then there's an edge where this data gets aggregated. And then the core cloud, where this data turning into information, turning into knowledge, turning into wisdom, is happening in this flow of information that is coming from one end to the other. And the big transformation that's happening in front of our eyes is that whereas this year all the data is produced by my teenage kids, going into the future the data is produced more and more and more by machines. Video surveillance, endpoint, IoT, self-driving cars, machines producing more and more and more data, and that we need to adapt to. Natural streaming data is going to be a very large part of what we have to deal with. So here is where the problem is. So today, the amount of data stored is still substantive. It has gone from 5 zettabytes to about 12, 13 zettabytes by 2023. But the data that is produced is very large. The 100 zettabyte we are talking about is produced, but it is not stored. That data is valuable. That data today is transient, it is leaking in the pipes, it's not being stored anywhere, it is considered not valuable data. But by the nature of it, as you know, there is gold in the data. The more the data that we store and work with, the more we are able to do something useful with it. But the problem, of course, is that our storage ecosystem, the cost, the benefit, that hasn't happened yet. For us to be able to store that growing 100 zettabytes, we still need to figure out how to scale our technologies. How do we produce higher density flash and other storage devices? This is what I call storage Darwinism. If you don't scale, you don't survive. And if you catch the obvious, the armadillo up on top has survived, it's got plenty of scales. That's the engineer joke for you. But you can see the scaling problem. Capacity hard drives today are a fast scaling device, believe it or not. Nobody talks about them. That's growing at 35% year over year. That capacity hard drive is keeping up with flash scaling, and in the data center, a vast majority of the data is still stored in this vast, growing, fast-growing hard drive. Of course, SSDs are growing faster at 44%, but you can see the vast majority of the data is still in hard drives. And at the bottom, you see the tape drives and optical drives and all of those that don't scale, that will continue to shrink as a percentage of overall use as the time goes on. So the basic mantra is, if you don't scale, you don't survive. Okay? So what did we do to scale? This is a picture I'm very proud of showing. From 24 layer to 48 layer to 64 layer to 96 layer, year after year after year, almost on a 15-month cadence, we've been doing this. The next generation is coming very shortly thereafter. This scaling, this growth in the skyscrapers behind, has been happening very systematically. However, as pretty as this picture is, this is the standard magician's trick. The action is not here. This is where all of the eye goes in. This going higher, taller, more layers is very nice to show. But remember, it costs a lot more to build those layers up. This is what I call linear scaling. Linear scaling is empty calories. Linear scaling does not produce cost reduction. You might as well start more wafers. You can add capacity, you get more bits. So what do I do when I just say that I keep adding layers? And here's an interesting statistic. The Salesforce Tower in San Francisco, and per floor cost of one layer of 64-layer NAND, the Salesforce Tower, by the way, has 61 floors, approximately same cost per square foot to build a next layer. About $800. You don't call skyscrapers scaling. That's just linearly going up. If you add more floors, it'll cost you more. That's the reason everybody doesn't build 200-layer buildings. So we do have a problem here, where everybody talks about, oh, I'm going to go to 100 layers, 200 layers, 300 layers. That alone is not the answer. The answer, of course, is that that is a multiplier. That straight going up layer, that Z direction scaling is the multiplier. The interesting action happens within. How do I shrink? For example, going from 48 to 64 to 96, in that time, the density of memory holes has gone up by 10%. Not much, but now when you multiply by the Z, it gets to be substantive. That's the trick in there. You do need to figure out how to scale in the X and Y directions. And you can see what happens. When you take that X and Y and now multiply by the number of layers, you're starting to see the real effect of it. The 10% effectively you can't even see, where you now start to see the effect of memory holes times the number of layers. And now you add on to 3 bits per cell. Oh, now we are talking real action. That 10% added to the 64 layer and multiplied by 3 bits per cell. So that's a logical scaling. So you now started with X and Y scaling multiplied by Z and then multiplied by the logical scaling. As you would expect, as we've all been talking about, we need to get to 4 bits per cell. The 4 bits per cell on that, so it's essentially adding 4 people to stay on that one floor where the elevator hole comes and reaches that floor. You got to store 4 bits in that. It's tough because read and write now get a lot more complicated. Write in particular, to be able to sense the 16 levels, arrays plus those 15 levels to be sensed in that same VT window gets to be a lot more complicated, so write performance starts to degrade. QLC is wonderful, but you do have the write performance degradations to go with it. But you can now see where we are getting the scaling from. We are getting from the scale from the fact that you get the memory hole density that is going up by 10%, but then you multiply by the number of layers times QLC, you end up from that 1.1 becomes 422 bits on that one vertical memory hole. That is the power of the scaling, why the industry is growing so fast. You know what you would like to do. You would like to have 5 bits per cell, but you can now start to see the diminishing return on this. The scaling benefit becomes relatively useless. For me to get to 32 levels that I need to sense, for me to get a 25% scaling benefit and the attendant degradation in performance. This is our basic problem that we need to deal with. So the 4 bits per cell will, of course, be our mainstream workhorse over the long term. If I use the same time scales as what happened in 3 bits per cell, we now see that retail 4 bits per cell already is out in the marketplace. You're starting to see the low-end needs 4 bits per cell is already out in the marketplace. But the difference between 3 bits and 4 bits is that at TLC, mobile was the next leader. Mobile took a big volume, then followed by client, then followed by enterprise. In 4 bits per cell, we see the reverse of it. From retail, the first place it goes to is enterprise. Then client, maybe at the same time, and mobile. So the idea is that by 2024, 2025, we are going to be about 50% of all bits shipped will be 4 bits per cell, QLC. This is nice to say, but of course, there is nothing called a free lunch. Something's got to give. We are all making the same kinds of design choices. The number of planes you can excite at any given time. But when you add number of planes, the die size increases. If the die size increases, I can't fit in a package. When I power up more planes, power gets worse. We would like to keep the page size the same, not keep growing the page size. So with the number of bits per cell, if you now come back and say, ooh, we are going to have a problem here. Will every application have that right bandwidth degradation that you're going to see? What am I going to do with it? So this is the point at which me as a semiconductor guy cries uncle. I said, I need help. I need help from someone smarter than me with respect to the systems, and I call Chris Berge. Chris, would you please come and tell me what are you going to do with this problem?
Smarter than you, Siva? I don't know about that, but let me give it a shot. Thank you. So if I understand correctly, Siva, basically we've got a technology that enables scaling, offers a very good cost TCO benefit, great read performance still with the QLC cell, but we've got some limitations on the right side. Well, fortunately, we've seen this before. On Western Digital's HDD business, we actually fought some similar issues with the physics of the magnetic media, and we had to move to something called SMR. SMR is shingled magnetic recording. So if you'll let me flash up one HDD slide at the Flash Memory Summit, I'd like to just explain what SMR is. So with shingled magnetic recording, what we do is we actually format the disks such that the magnetic bit regions start overlapping, much like shingles on your home. And in construction, when the builder is putting together your roof, it's a perfect. They just go down the row, they start working from the bottom of the roof up to the apex of the roof. But for those of you who do some DIY in the audience, you understand that when you try to replace a single shingle, it's difficult. And thus the challenge we have on SMR media with random write patterns, where we're trying to do an insertion of a write. The good news is that we think we've solved this problem. SMR has now been commercially available for almost 5 years, and we believe we're on track for 50% of the HDD bits. The large market that Siva showed was growing considerably at a 34% CAGR, to actually represent 50% of the bits that the industry provides to data centers. So Western Digital played a big role in creating the ecosystem to allow for this intelligent data placement. So let's just talk a little bit about where we're at from the evolution of the data center. The valley here has been energized over the last decade with the emergence of the hyperscalers. We have seen their sheer scale, their veracity for data to compute, to collect, to analyze, and monetize data. However, if you look at this evolutionary path, as these data sets began to grow, you can see that we had to start bringing in new types of computing technologies, where general purpose wasn't the best solution anymore. And so we've seen this nice evolution of all these new types of processors that could specifically target these new workloads that were swamping data centers. Now, on the storage side of the equation, yeah, we did our typical thing. We moved to faster interfaces, and we reduced some of our overheads and legacy protocols, but we really didn't change a lot. This is what needs to occur. Storage architectures must become purpose-built. Enter zone storage. The storage evolution required for this journey through the Zettabyte age that Siva articulated so well. In order to deal with this Zettabyte age, we need to step back and we need to architect a storage tier that can take advantage of the compute aspects of today. We've got VMs, we got multi-tenancy, we have serialized sensor workloads, and we've got tremendous amounts of video. The industry needed an open source, cloud-friendly stack that databases could format data in a media-friendly way. Western Digital played a critical role in open sourcing, coding, and standardizing what this ecosystem needed for the adoption of SMR HDD storage. And now, as an industry, we're extending that support and zone concepts to NVMe storage through zone namespaces. So what does a ZNS or zone namespace SSD have to offer a next generation data center architecture? Actually, quite a lot. First, we've reduced the cost of the drive. We've significantly reduced the amount of DRAM content in the drive through the simplification of indirection tables. Then, we reduce the amount of over-provisioning required by leveraging the system-level serialization and knowledge of data groups for intelligent data placement in the drive. Beyond this, we provide next-generation features that are purpose-built, considering the concepts around VMs and multi-tenancy. In the end, we end up with a drive that enables tremendous read performance, the right TCO, smart write amplification. It's so, so sweet. So if we go back to our challenge state, what we actually see is that zone storage enables us to take this limitation through management and actually transform it into a strength, providing the data center with more value, allowing for the scale required moving forward. What about tomorrow? Well, we know today that we're in the early innings of this onslaught of data. We're experiencing tremendous amount of sensor data, sequential data, looking for read performance for future analysis. Well, we've got that one covered. What's critical for ML, deep learning, inference data sets? Massive data sets, amazing read performance. We've got that covered too. What about the emergence of serverless or function as a service? Well, we need multi-tenancy. We need isolation. We've got that too. So zoned storage really sets up the industry for the future of data center architectures. So hopefully you're as excited as I am, and the Western Digital team is, about this journey that we're starting, and that as Western Digital, we've been on for quite some time. We are welcome to come over to the Western Digital booth, where we're demonstrating our ZNS NVMe development platform for those of you who want to start your design and start this evolution to zone storage. Secondly, we've introduced our purpose-built NVMe SSDs with a mixed workload SN640, based on our 96-layer technology, BiCS4, as well as our SN340, a reduced indirection SSD, a data orchestration-friendly SSD for customers who have already started this write management journey. Third, we have our SMR HDD platform, very complementary as was discussed today. And then last but not least, we have our zone storage industry initiative, Zone Storage IO, where you can go and find the tools, the code samples, and the architectural educational information to help you to start the journey of zone storage. So in conclusion, you can see the exciting data center journey we are on with the pervasive adoption of zone storage, leveraging and converging the best HDD and SSD product capabilities, being friendly to the physics underneath these products, and are uniquely architected for tomorrow's unique and overwhelming data sets. We're truly offering industry innovation through intelligent data placement. Please join us on this journey. Thank you.